Okay, begin. All right, thanks, Gizem. The stage is yours.
Okay, so thank you so much. I appreciate the effort of putting together such a school. So I thank the organizers for inviting me to be a part of it. And so welcome to this graduate series lectures on the Suture representations in primordial cosmology. Now we will go backwards in the title. First, I will make use of primordial cosmology to tell you about why, in fact, we are interested in the Suture spacetimes. So the first message to focus on will be that this is a spacetime that we do encounter in our universe. And as the lectures go on, the title, like we will have described more and more of the concepts that make up the title. But so to begin with the primordial cosmology part, and in fact, the cosmology part. So cosmos is a Greek word that means harmony and order. And so cosmology is a field in physics that studies the history of our universe, tries to put it in an ordered, harmonious picture. And for the first lecture, we will focus on the Suture geometry. But before we get to that, let's just consider some observations about our universe. And let's start with pre-technological times. So say we have nothing except just our eyes and ears and hands and stuff like that. And the first thing we notice that we don't even talk about because we are very used to it is the fact that within our day, we have the concept of morning, like daylight time, and nighttime. So there's the sun, whose light brightens our sky in the morning times. And then at night, there are stars. So some bright objects, but also some concept of darkness. So let's say dark and light. Now, if we move on a little bit in history, we learn from Copernicus, Kepler, and Galileo to think about our universe such that there are no special points in it. So a point here is not very special than a point there. Of course, this means at very large distances, like there's the sun, which is a very dense object, and then around it is some emptiness, not so dense, and then there's the Earth, stuff like that. But if you look at the scales larger than galactic scales, it looks like galaxies are distributed everywhere evenly. So it's no special points at such directions. And at such distances, such scales. And then also there is no need to think about any special directions. So this existence of no special points is called homogeneity. And this all directions being treated equally is called isotropy. And we understand our universe to have an infinite size. Now, if we come to think of our universe as an homogeneous and isotropic place that has infinite size, that has stars and dark nights. Now, if we think a bit more on these concepts, it means being homogeneous, there's stars like almost everywhere in very large distances. And if we are an observer on Earth, we will see a star in every direction we look at. Now, even if our point of sight does not end on a star at this radius, we will see the one at the next radius. So like there's all these infinite radii around us covered with stars. Now, so this goes to infinity. If it has been like this always, if nothing changed over time, this means this would mean for an observer, every line of sight ends up at a star. And so you will have all these light even at night. So you will not have the concept of darkness, which was our first observation that we have even without any technology. So this means there needs to be something more. Now, you can think of a couple of solutions, but the most logical one is that if the distances between these stars are changing in time, then that means because light travels at a finite speed, there will be some stars so far away that light hasn't had enough time to reach us. And then, and also like if this, if there's curvature and things are changing over time, then, okay, you only receive, even though you live in an infinite universe, you only receive light from some finite amount of stars. And that gives you that can give you a dark nighttime in a homogeneous and isotropic universe. So this paradox of having dark night sky is called Albers Paradox. And so the resolution is to consider that there is evolution over time in the universe. That's the universe evolves over time. It has a finite age. Its geometry might be changing over time, but time is important. Now, if this would be your very first introduction to cosmology, a nice exercise for you today would be to read, there's a nice book by Barbara Ryden called Introduction to Cosmology. And if you just type in the title, you reach it. Like even I can reach it from Prague. So that means it's pretty much open access. So you shouldn't have any problems reaching it. But this is a good, and it's in fact an undergraduate friendly book. And so you can just read the first chapter. If this was your very first introduction to anything about cosmology. Now, so we came to this through some thought process, but then technology develops. And around 1929, Hubble so Hubble is an astronomer. He looks at a special kind of stars called Cepheids. Within astronomy literature, their absolute brightness is known. So if they look dimmer than what you know their brightness to be, it means they're farther away than you. So by looking at how bright these special type of stars look, you can measure their distance from you. And he makes these measurements over a lot of stars. And what he notices is that they're moving away from us. So the universe is expanding over time. So now we even have, at year 1929, we even have an observational evidence that we live in a universe where dynamics over time is important. And this rate of expansion historically is called Hubble parameter, just to recognize his name, because he was the first one to make these observations. And we show it by age now. But now, okay, so we acknowledge we live in a dynamical universe, and we want how to put in isotropy, homogeneity, and all this dynamicness together. How will we describe such geometries? We will make use of the metric. So this means an infinitesimal distance between very two nearby points on the geometry of interest. But this is not just a geometry with spatial sections. There's also time involved. So we will have time direction and spatial directions, as many as you want, but in our world, we are aware of 4. In our, in the scales we can access. And so now isotropy means each of these, okay, so in the metric, these enter as unit distances in every direction, enter like this. Okay, so in my notation, minus sign in the metric goes with the time direction and plus signs go with the spatial directions. And we are working in units where C is 1, in natural units, so H bar is 1 and all that. Now dynamicness means there is some function, there is some time-dependent function involved in the metric. But if all the space, so some like, there can be some, so for dynamicness, time-dependent functions, okay, over time. Homogeneity means such functions only depend on time, not on position. So something changes over time the same way at every point, okay? Isotropy means, so it could be, okay, so we can multiply all these directions by some time-dependent function. So far this is homogeneous and dynamic, because there is some time dependence, but no spatial dependence. Isotropy means all these functions, I mean, this at every direction, whatever this expansion is, whatever this dynamicness over time is, it works the same way over spatial sections. So in fact, these are all the same amount. So now it could be that there is some curvature. So far this is just flat, but a more general way is to have curvature involved. So let's just call this some spatial sections. Okay, so now this is an isotropic homogeneous dynamic metric, and it's named as the Friedman, Robertson, Walker, Lemaitre metric after the people who first came up with it. And in fact, this sets the basic assumptions of cosmological backgrounds. Okay, so this is the kind of space-times we work in. But now, so the Hubble parameter we introduced is actually the range of change in this factor. This is called the scale factor. Let me use a different color. It's the rate of change of time in the scale factor. Now, it doesn't need to be that the Hubble parameter is the same function over all time. The universe can go through different stages in its history. And in fact, around 1948, it was told that the beginning of the universe was a hot, dense state. So it means the components of the universe were light and light-like things, very light, almost massless things going at relativistic speeds. And in such a universe, as this universe expanded and cooled down, it could, through particle interactions, it could form light elements. So this is hydrogen, helium, and lithium. And this hot dense phase is called radiation domination. Okay, so later on, of course, today we do not live in this hot, dense state. At some point, galaxies form, stars form. So that's called matter domination. So at like early 1950s, it was thought that the universe started from a radiation-dominated stage, and it moved on to matter-dominated stage. So the Hubble parameter during radiation is different than the Hubble parameter during matter, for example. But in such a radiation domination, you can only produce, I mean, these like elementary interactions can only give you hydrogen, helium, and lithium. But you know, we have things like oxygen, carbon, a lot of heavier elements. And it was worked out that the conditions suitable to produce these heavier elements take place in stars. So to produce heavier elements, you need to first produce stars. And to produce stars, you actually need to first produce things that will lead to galaxies. Now, so it became important to understand how did stars form. How will stars form? And as that question was being considered, in 1965, there was an observation. Two antenna scientists built up an antenna. So it's just like, just a radio antenna built for communication purposes. And they need to do some measurements to, you know, to understand like the catalog, the standard thing of their properties of their antenna. And with their antenna, because of the frequency it was sensitive to, they picked up a signal at every direction. And this was in the microwave range at every direction. So this was an observation. Now you have like a very solid observation on isotropy. And later on, more, so this was an observation by chance. The equipment was built for something else, but it came across this signal. But then the signal was suspicious. So instruments were built, and you know, thoughts on how to analyze these things were developed just for the purpose of observing this microwave range frequency radiation. So this type of instruments were developed further, and this signal is now known as the cosmic microwave background radiation. So it's shortened into CMB. And today a lot of things measure this. So it's the famous ones you might have heard of. Like Planck is the most famous one that operates today. There was BICEP with some catastrophic events, but anyway, so there's a lot of measurements on this. And what it measures is it looks at temperature perturbations. So it measures temperature in the sky. At all angles, it picks up a reading, and it's pretty much the same. There's like very little deviation from spot to spot. So there's your observation for homogeneity. It's almost evenly distributed at every point. And they are not like grouped only in one direction. They're at every direction. So with these CMB observations, now you also have like very solid proof of isotropy and homogeneity in the universe. But then what is this? Like, what is creating this radiation? What is its source? Is the new question to ask. So up to now, from our basic or like observations growing as our technology grows, we have the question of how are stars forming, and we have this suspicious cosmic microwave background radiation. And we think that the initial stage of the universe was radiation domination. Now, in 1970s, a bunch of scientists, so they worked in groups, they worked separately, but these are the leading names that gave a lot of thought on this, is Zeldovich, Sanyev, Harrison, Pepples. And they worked out conditions such that density perturbations. Okay, so where are you going to form structures? It's through gravitational collapse. So there needs to be, okay, everything is overall homogeneous, but if there's a little bit of an so if in some spot, the density is a little bit more than what it is around its region, it can start to undergo gravitational collapse. And through this, it can create bigger and bigger structures. So it can lead to formation of galaxies and stars in those galaxies, things like this. But in order for this gravitational collapse to be successful, to develop structure, we are living in an expanding universe. So this collapse needs to overcome that pulling apart effect of the expansion, background expansion. And everything is homogeneous and isotropic. So, it needs to overcome all that. So they calculated that in an expanding isotropic and homogeneous universe with small density perturbations, these density perturbations can overcome the expansion around them, and through gravitational collapse form bound structures if they have a flat spectrum. Now, what does it mean to have a flat spectrum? Now, these density perturbations are scalar quantities. This means, like, if you think of how things transform under rotations, you have scalars, vectors, tensors. So in that sense, they're scalars. And so you can calculate them starting by studying scalar fields. And it turns out convenient to work in momentum space. So this means you have a field that has space and time dependence, but you decompose this in terms of Fourier modes with some factors of pi. We are not very careful about. We want to be very careful about right now. So, and you consider your calculations on this. You can do this Fourier decomposition because you can you can treat every direction the same. So because of homogeneity and isotropy, it lets you talk about these momentum modes. So these are called momentum modes. And do your calculations in momentum space, so in this coordinate momentum space, instead of position space. And you look at their 2-point functions. So this you can do, so this would be the calculation we would be doing if this was a lecture on inflation. And you can do this through canonical quantization, through wave function quantization. There's a lot of details you need to think on. But because this is not our purpose here now, just take it that this the spectrum is the 2-point function of these scalar fields. And it turns out that what contributes non-trivially are momentum modes with opposite momenta. Okay, so there's a direct delta function. And then there is some piece that is dependent on the, the length of momentum. Now, so this piece is the momentum dependence. Okay, so the directionality you handled, and separately you handled the overall momentum dependence. So from this momentum dependence piece, you define a dimensionless power spectra. So it's just this factor of k to 3. And you say, on the whole, this has such a shape. So overall, so you parameterize it, check parameterization. It has some amplitude, and it has some momentum dependence, which if you make a measurement, you will measure it with respect to some reference scale. But it has an exponential dependence on this momentum, on the momentum, so exponential dependence, okay? And even this exponent you parameterize as such. Now, if the exponent is 0, if ns minus 1 equals 0, it means it doesn't matter at what momentum you are asking, like every momentum contributes the same way to this 2-point function. So that's the flat spectrum. And in fact, with this parameterization, this is the way that the analysis for the observations are done. Of course, like there's a lot of different technicality that goes into it. But for example, the quantity over which an observational person and a theoretical person can talk, can discuss on is this thing called NS. This is called spectral index. And those CMB observations constrain the value of this. It means they don't tell you things like ns equals 10, ns equals 1. It means they tell you ns equals less than 0.9, something like this. So it gives you a range that is feasible. But so this is what it means to have a flat spectrum. And in fact, this is something you can measure. So this was needed to have, to be able to form galaxies on an homogeneous isotropic expanding universe. But now it turns out that you cannot have this in radiation domination. Cannot have this in radiation domination. Now, by 1982, Hawking does a calculation of scalar fields on the Suture. And he shows that if the scalar is massless, this quantity for momentum much less than this Hubble parameter, this quantity comes like this. So k to the exponent minus 3. Now, if you look at your dimensionless power spectrum, there's a K3 piece coming from the definition. And so this is the K dependence of this, what we define the power spectrum. And then there is this K to the minus 3. So overall, for a scalar field, for a massless scalar field on the Suture, you do get the flat spectrum. Now, so you cannot have this on radiation domination, so there needs to be something more. And that something more, at least ideally, seems to be a de Suture geometry for the beginning. Now, by this time, also, there's a lot of other motivations to consider an era of accelerated expansion for the initial state of the universe. So up to some point, we thought the universe started in a radiation dominated stage, But then through more analysis, it turns out that you need to extend that history. There is something more in earlier universe. And this era of accelerated expansion in the early universe, it's what's called inflation. But this can lead to the kind of initial conditions, that means flat power spectrum, that can eventually lead to formation of large scale structure, that is like clusters of galaxies and galaxies in them. Now, when you do inflationary calculations, and okay, so there is a lot of observational evidence for this to do with CMB measurements. Now, when you do inflationary calculations, this scalar field, you split it into a background, a homogeneous background, plus perturbations around it. The scalar field, how to say this, affects the geometry. So instead of just the this A of t as a function being whatever it needs to be in an accelerated expanding era. So it actually is like this. This is just the background. This was the Friedman Robertson Walker background, but because the scalar field affects this geometry, you get extra terms. Some more. There is some. Okay, so all these extras, these are called metric perturbations. And when you do these calculations, you have to watch out for general coordinate transformations. Now, so this means you take time and you transform it to some something that depends on both position and time. And you also do these kind of things for the spatial sections. Under these kind of transformations, now what we call the background will not stay the same because it has explicit time dependence. So when you change the time coordinate, what this is changes as well. So you have to take this into account on such a background transformation. On such a background, what are the transformational properties of perturbations? And also like how you define what you define your background to be. And how are things constrained such that your theory, your Lagrangian is invariant under these transformations. Now, this is the kind of symmetries you need to take into account when you do cosmology, and when you do inflationary calculations. This Hawking's calculation of a massless scalar field on the Suture, here, the scalar field is not affecting the geometry. So there's a bit of a difference between an, how to say, almost inflationary calculation and a calculation on the Suture. But even so, in practice, you calculate things on the Suture, and then you know how to, in an educated way, how to keep track of this this difference, okay? So we will focus on the Suture spacetime as an ideal case of accelerated expansion. And if you want to know more about this inflationary calculations, there's a lot of nice lecture notes on inflation given in thesis schools. So these are by different people. There is one version by Baumann, there is one version by Senatore, and they tell all these modern techniques, modern problems and modern techniques that go into these kind of calculations. But so this is what I mean when I say we take primordial cosmology as motivation to study de Suture. So for us, this is just the ideal case, but even asking questions on ideal case gives us important information about even for inflationary things. So when we do this, we will be, how to say, our guide will be the Suture symmetries as opposed to general coordinate transformations. Okay. Now, if we put together the history of the universe we know of so far, we are aware of an early era of inflation. So when we began our introduction, we thought the beginning of the universe was radiation domination, but then it turned out that there is an inflationary phase. Now, inflation creates galaxies, fine, all these scalar density perturbations, but then we don't just have scalars, we have fermions, we have electrons, all those standard model particles. So there needs to be a stage where the energy density from the inflation gets transferred to some other fields. This is called reheating, and depending on what kind of an epoch you take it to be, if it depends on parametric resonance, it's a preheating epoch. So there's this, I put a question mark because there are not any direct observations about this epoch. But okay, but then, so we move on to radiation. This is all light elements, light things at relativistic speeds. Then we move on to matter. So this is where galaxies dominate, let's say. And in this matter, there's also dark matter. And then through observations, it turns out that today, again, our universe is undergoing an epoch of accelerated expansion. So we don't know what causes this accelerated expansion, so we call it dark energy. So there is two epochs of accelerated expansion, one in the early universe, one in today's universe. And for both of these ideal versions are the Suture universe. Now, the way you set up questions in an inflationary universe and the questions in a dark energy universe is a little bit different. And this also works in, and this difference is even at the level of coordinates you use, which is actually what we will consider in the rest of the lecture. And so from a technical setup, the goal of this lecture series is to stick with coordinates with the part of geometry that is accessed during inflation. That's why the title is the Suture representations in primordial cosmology. But so with this motivation that we do have the Suture-like epochs in the history of our universe. So this is very physical. Even though the de Suture version is an ideal version, it is something to take into account. The big question we are faced with is how to set up physics in a de Suture universe. Now, so this is a graduate friendly series. But now the definition of a graduate can change a lot. You might be at the first semester of your master's or the last semester of your PhD. So hopefully there will be something for everyone. But in the first lecture, we will focus on the Suture geometry, and this is very general relativity based. It means if you want to, when you go home, if you want to repeat a calculation, you will need to know like these covariant derivatives and some things from general relativity. Lecture 2, we will focus on the Suture symmetries. This will be quantum field theory and group theory based. But I mean, this is fine to understand even if you did not see quantum field theory, but you had a very strong quantum mechanics course. And lecture 3, we will focus on the Suture representations. So again, this is quantum field theory and group theory based, but we will use this as, we will do this in a way where we will be motivated by holography. When the time comes, I will describe to you what holography is. But for now, take this as a modern contemporary tool in gravitational physics. And hopefully, depending on how fast or slow we are, our goal would be to see at least one example in such that you see worked out realization of these representations in a setup that is the setup that you start with in inflationary calculations. Oops, sorry. Okay, so now we actually start with the Suture geometry. So what is this geometry that we saw that we cannot get away from? We need to face it. It's a fact of our reality. So this is a solution to Einstein's equations with a cosmological constant. This is the cosmological constant. Such that this cosmological constant is positive. There is other solutions with different signs of the cosmological constant. If you solve these equations for lambda equals 0, you get Minkowski space-time. This is just flat space-time that you encounter in particle physics. And if you solve this for negative values of the cosmological constant, you get anti-de Suture space-time. Now, de Suture is the name of the person, and it's this geometry was first, written down as a solution by this person. Hence, the name is de Suture. But the practical property of it is that it describes a universe that expands. Now, this negative sign cosmological constant solution describes a universe practically, from a practical point of view, that contracts. So it does the opposite of a de Suture-like evolution. That's why it's called anti-de Suture. So in some things they are the same, but also in some nuances there is differences. Okay, so, and this is a maximally symmetric solution. Now, towards the end, we will visit all these adjectives, this grouping in terms of cosmological constant and mentioning maximal symmetry. We will focus on de Suture for the majority of the lectures, and then we will have learned some things. And then in the end, we will come back and look at these adjectives to see where de Suture fits in the bigger picture. Hopefully. This means in a given number of dimensions, it has all the amount of symmetries you can have in those dimensions. And these other solutions with other signatures of the cosmological constant, these are also maximally symmetric solutions. Now, how to describe these? So actually, I am compiling a list of references for you to be shared with you. But so there is even more references than those I mentioned during the lectures, but I point out to the most important ones even in the lecture. So whatever we talk now, if you want to go back and read more on it, there is these lecture notes by Hartman and so one set of lecture notes by Hartman, and then one set of lecture notes developed through some Lesuge schools, a school like this one, by Strominger and others. There's a recent PhD thesis by Ruben Monton, and there's a paper by Aninos called the Suture Musings. So the first three, so Hartman, Strominger, and Monton, these describe the kind of coordinates we will describe now in great detail. And this last one is a piece that discusses the Suture in different coordinates, but also the Suture-like geometry. So some like the Suture black hole-like geometries as well, for example. And it describes contemporary problems on these geometries. So these are good reading material if you want to develop more of this background. But so to start with understanding the geometry. So to understand the geometry, we look at the metric. But over what set of coordinates will we look? There is a set of coordinates that covers the whole geometry, the whole of space-time of interest. These are called global coordinates. Cover the time. Space-time. So the global coordinates, the Suture in terms of the Suture global coordinates has the following metric. It has a time-dependent piece that as a function is the cosine hyperbolic function. And it has its spatial sections. So remember, these are all things that come with the plus sign. So these are all the spatial sections that take place as spheres. Now, if you look at this cosine hyperbolic function, from this t runs over all time, so minus infinity to infinity. From 0 to plus infinity, the value of the cosine hyperbolic function increases. So from time 0 to future, the spatial sections are spheres that are growing. From 0 to minus infinity, so from now, if 0 is your now, to your past, okay, let me say it like this. From minus infinity to 0, cosine hyperbolic function decreases. So this would be a sphere that is shrinking towards T0, this capital T0, and then growing again from T0 to future. So because of this growing nature, this is the accelerated expansion part of the geometry. This is why, so it's because of the behavior of this cosine hyperbolic function that the Suture describes an accelerated, a geometry that undergoes accelerated expansion. Now, one way to think of this geometry is so curved space-times, you can think of them as embedded in flat space-times of one dimension higher. You can do this with the Suture such that you take the Suture in dimensions of your interest and you embed it into a Minkowski in one more dimensions. So it means you just add one more spatial direction. There can be other embeddings where you add one more time-like dimension. So this is a bit, this matters. And then the Suture, so this is one dimension more than what we want. But in this one more dimension, so you need to bring it down to one lower dimension. So you put in a constraint to take care of that extra dimension in a sense. So you describe this d+1 dimensional de Suture as a hyperbola in this d+2 dimensional Minkowski. So these coordinates, so all of these coordinates, when you add them up like this, they just give a constant value. This is constant. Now, this is one thing to say. Remember, we introduced h of t, Hubble's parameter. Hubble parameter. For the Suture, this is a constant. If in inflation, it has very big time dependence. But now, okay, fine. So this is the equation that describes our surface. But what is the surface? What are the coordinates? What functions can you write in place of these xa's such that they satisfy this red equation or this blue equation? Now, consider embedding two-dimensional de Suture into 3 dimensions. Okay.
Can I ask a question?
Yes.
You wrote that we can consider the de Suture as a time-like hyperbola. How can we consider a 4-dimensional space as a curve, speaking mathematically?
Okay, now we are doing that.
Okay.
Just listen carefully, and if this doesn't make you happy, let's see. We will see if this makes you happy. But so this is the curve, okay? This is our curve. And be careful where we are doing a contraction where the metric is such that the 0th component has a minus. So actually this equation has the x0 component contributes with an overall minus. So this is our equation. Now, if you look at what this equation says for x0 equals 0, so at time, what would be the global time equals 0, this condition, this constraint gives you x1 squared plus x2 squared equals a constant. That's the equation of a circle. So at constant time, you have circles. Now let's take a constant space direction and put it to 0. So one of the spatial things to 0. Then you're left with something minus squared plus something squared equals a constant. That's the definition of a hyperbola. Now, if you plot this, now we go even 1 dimension lower. So just minus x2 squared plus x1 squared, you get this shape. So this is the sections. This is the geometry of these sections. This dimension. And now how to write these coordinates, coordinates on this hyperbola. You just, in an educated way, construct this based on properties of hyperbolic functions and cosine hyperbolic functions. It turns out that, so you put these hyperbolic and cosine hyperbolic functions, like one to the time-like direction, the other to the spatial direction. And also the spatial directions have components on sphere, depending on how many dimensions. So if you just have this DS2, I mean, in the least case, this would be just a theta angle, okay? So in one spatial dimension, this would be just angle theta. In 2, it will be like theta and phi, things like this. Now, for example, for DS2 to embed it into, okay, so you have two directions on the sphere. So to embed it into R12, so this is three-dimensional Minkowski, you need a two-sphere. You can parameterize it as follows, and you can write these hyperbola coordinates as follows. Now you can check, you can just take like all these sinh square HT. This is cosine square theta 1, all these things. So you will add these two. When you add, so there's an overall cosine square parenthesis. So adding in that parenthesis, these two gives you 1. And then you are left with minus H1. So there is something like minus sinh square plus cosine hyperbolic square. That again gives you 1. So indeed, these coordinates do satisfy this hyperbola equation. You can check this. And once you have this, so this is the way to describe it. And now once you have this, we want the metric. So we need to compute their infinitesimal amounts. So you just take derivatives with respect to all the variables you have. So in this case, there's the t and theta 1. So you actually have just two variables. And when you add the, let's see. You end up with this metric. Okay. So, this was the form, anyway, we wrote in general. So we just obtained a two-dimensional version of this. In which case, this is just the metric. This is just the metric on S1. In more general dimensions, the metric on the d-dimensional sphere goes like this. It's a lot of sine squares involved. And you can try for yourself. So for four-dimensional de Suture, embed it into five-dimensional Minkowski. This is the coordinates you need to make use of. And you can do all of that. Like you can take their derivatives and you end up with this metric. So it's like you are looking at one higher dimensional geometry. Within that one higher dimensional geometry, you're looking at something constant surfaces, like this something constant, in this case being the hyperbola equation, this for example, this satisfying this equation. So in a d+2 dimensional flat space-time, you're looking at constrained d+1 dimensional surfaces. Or like you're looking at constrained surfaces within that d+2 dimensions, and that gives you the metric in d+1 dimensions. But this is how the embedding works. I hope that also helped with the question. But once you come to this stage, now because all these spatial things are actually angles, they just range over 0 to pi or 0 to 2 pi. And then you have the time direction from -infinity to +infinity. Now we can compare this. So this is with the Friedman-Robertson-Walker metric. Again, it is isotropic. There is no, so this is only time dependent. And it's in front of every direction. So homogeneous and isotropic. It has the overall form like a Friedman-Robertson-Walker metric. But we said in the Friedman-Robertson-Walker metric, the spatial sections in general could be anything. So they could be open spatial sections. So this would be hyperbolic sections. It could be flat, that's just RD. And they could be closed spatial sections. So they would be spheres. Now here we have so because the Suture metric matches this general form of Friedman-Robertson-Walker metrics, so DS is one special case of Friedman-Robertson-Walker metrics. And because the spatial sections are spheres in global coordinates, it's the Friedman-Robertson-Walker metric among closed spatial sections. This is in global coordinates. Now there's another set of coordinates. And in fact, this is the set used in primordial cosmology. Remember, the point was to find functions that can realize these capital X coordinates such that they satisfy that hyperbola condition. So there can be, this was one way to realize them, but that doesn't need to be the only way. Another set is like this. So in this case, you have, for your time, you have T, and then you have these coordinates on the sphere denoted by Y's. Now, if you look at this set of coordinates, so there's these exponential factors that depend on time, and to the x0 and x1 coordinates, they come in with opposite signs. So actually, Y's can be anything, but this set of coordinates are such that x0 plus x1 equals this 1 over h sinh plus cosh. And well, at the end of the day, these are exponential functions like this. So actually this combination is just exponential e to the ht over h. So exponential to something. Exponential to something will always be greater than 0. So this set of coordinates not just satisfies that hyperbola condition, but it has one more condition, x0 plus x1 greater than 0. And yeah, sorry for the smallness of the shape. But you can, so on our hyperbolic sections, you can draw this x0 plus x1 equals 0 line. That's the orange line. And everything above it is what's covered by our planar coordinates. Planar patch coordinates. So these coordinates cover only half of the space-time, but they cover all the future, you see. Now, again, I have given you these expressions. So you can again work out, you can take their differentiation, like you can differentiate them and compute the metric with this coordinates. And this is the metric you arrive at. So here, time runs from -infinity to infinity again. So this is different. So the global time coordinate is different than the planar time coordinate. And note that it turns out in this set of coordinates, spatial sections are flat. Flat spatial sections. So this half of the Suture corresponds to the other kind of to a different kind of Friedman-Robertson loci in terms of the curvature of its spatial sections. This set of coordinates is also called, I said this planar patch, but this is also called the Poincare patch. Now, one thing we would like to understand, are there any special surfaces along, okay, not to say it like this, but maybe I don't draw the geometry, but how can I draw its general properties? Just to understand something general about the geometry at hand. There's a technique for that, a way to draw infinite sized space-times of any dimension and of any curvature on flat two-dimensional finite sized papers, on our papers. So these are called Penrose diagrams, and these preserve the causal structure. So when you draw lines on them, you see that if they cross, they will affect each other. But if they don't, they will not affect, such events will not affect each other. And on these diagrams, light rays travel at, so that also means massless things. So relativistic things, things travel at 45 degrees straight lines. So if this is our coordinate axis, light rays go like this. This just means either a right moving light ray or a left moving light ray. But basically, this is to do that. And then we will see some features of the Suture spacetime, which will be important way at the very end. But now this was our geometry, all of our geometry in global coordinates, where T is over an infinite range. So this is the problem, how to bring this infinite range time to some finite interval. But then in terms of spatial sections, we have spheres. So if I just write explicitly one dimension on the sphere, so this theta, if you like, you can think of this as the radius of the sphere. All the other dimensions are put together into a smaller dimensioned sphere. So I can say I will just consider T and theta plane, and know that each point on this plane is actually a sphere of d-1 dimensions. Okay, fine, but still this is an infinite plane. Now, there's a trick, there's a transformation. So we need to find some transformations that will bring these infinite ranges over finite ranges. Maybe, let's say, some intuition. Maybe this is good, not good, but right now, this global time is the argument of cosine hyperbolic function. Okay, So the arguments of cosine hyperbolic function are of infinite range. But for example, consider another function. If you consider trigonometric functions, or let's say trigonometric version of this, like if you consider, so yeah, instead of cosine hyperbolic, if you were to consider some cosine, say W would be over a finite range. Okay, so actually we kind of need to find a transformation like this that brings functions with arguments over infinite ranges to functions with arguments over finite ranges. To our luck. Now this Penrose diagram you can draw for any geometry. In fact, actually, maybe you are tired, so it's good to just take a 2-minute break. Now on this screen, there is this reactions section from where you can normally raise your hands, but you can also put a lot of other things. Can everyone just try that? Just make these other icons. Where's everyone away? Okay, so some people are doing some things. Now, I will ask those of you who have just seen a Penrose diagram of any kind to put up one of these. It can be for Minkowski, it can be for a black hole. I cannot see if everybody put something. Okay, so those who have seen a, okay, I see one person. Okay, so a lot of people have never seen Penrose diagrams, it seems like, or they could not find the icon to put. So good, so this is a general technique you can do for any space-time, or at least like the conventional space-times we encounter in physics, like Minkowski, de Suture, black holes, all these. But sometimes it involves a lot of subtle coordinate transformations. Sometimes you get it in one step. So luckily, in de Suture, we can do this in one step. Now, if we make a transformation like this, let's just take this. So now I forget these, just cover these spheres and just bring this cosine hyperbolic up front. And now if I define this as a new time variable, let's see, let's call all of this d tau. So in terms of this new time variable, I have d tau squared plus d theta squared. And then whatever this was is some other function now, depending on what tau is. Now this is the flat metric multiplied by something. This is flat metric, okay? This means I can draw this on my flat paper. Maybe, again, it needs an infinite ranged paper. We don't know yet, but at least it's some flat object. And also what I have done is I written the de Suture metric in terms of the Minkowski metric. Now such transformations, so metrics related to each other by an overall factor, are called conformal transformations. And we will have more to say about this later, but for now, just know the name. So this would be G mu something squared. This something can depend on coordinates, some other. So this is called a conformal transformation. But what we did here is we did one conformal transformation. And now what is our new time direction? We just need to do this integral. And it turns out that, so this was from, never mind the ranges, but it turns out that this new time and the old time are related to each other as follows. Now, remember the intuition I gave you already. We got some trigonometric functions. So tau has to have a finite range. Now, what is that range? So on this side, we knew that, sorry, this capital T was from -infinity to infinity. So in this equation, if you plug in T equals -infinity and solve for tau, it gives you tau equals -π/2. And if you plug T equals +infinity and solve for tau, it gives you tau equals π/2. So in one move, so now this is a finite, a coordinate with finite range. So we were lucky, in one move, we got to achieve a flat metric that was covered by coordinates of finite range. Now we don't need to worry about theta because as an angle already from the beginning, it was between 0 to pi. So now.
İntegral tau değil, tau olacak galiba. Güzel.
Bir daha söyler misiniz? Tam duymadım.
Theta eşittir integral var ya, tau olacak galiba.
Tam bu tau, bu t. Bunlar hep tau. Şu taraftakiler tau, şu taraftakiler t.
Ya sağ tarafta integral var, sol tarafta...
Burada da var integral.
Okay.
Şu integral işaretini yapmamış olmam mı? Evet, orada da var o. Okay, so of course we are integrating both sides. Now, okay, if we look at our coordinate system, we have -π/2 to π/2. Now let's just draw this. Actually, this is what the Penrose diagram is. It's a picture on the range of the coordinate system. Let's find the color. This can be tau. And this can be theta. So this goes from so this is theta equals 0 to theta equals pi. So the theta coordinates cover all of this range. And then sorry, this is tau. These coordinates cover π/2 to, π/2 to -π/2. Now, I could not draw it, like the measures are not good, but this is a distance of pi. This is also a distance of pi. So time coordinates cover all of this. And eventually our space-time itself is covered by this. That should be a square. It looks like a rectangle because of bad drawing, but it covers this range. Now, these theta coordinates are coordinates on the sphere. So actually 0 degrees is the, I'm doing this yes, 0 degrees and pi degrees. Okay, they don't, let's see. So this is your theta 0. This is your theta pi. So these are the poles of the sphere, north and south pole. But I mean, on the sphere, you go round and round. So like you don't fall off. It's not like a physical boundary. But these time directions, so these boundaries are time-like boundaries. And you know, that's it. There is nothing beyond that. So in these coordinates. So this I will denote by chi plus, and this I will denote by chi minus. But this is called the late time boundary. And this is called the early time. Boundary. So there is these, and these are physical boundaries. And now we're out of space. Now let's draw this nicer. So we have the Penrose diagram for the Suture. Let's try to keep it as a square. And there's these two time boundaries. This is late time. These are physical. And remember, we had another coordinate system. There was the planar coordinates. Oh, by the way, it's up to you to figure out what this function becomes. It comes out to be 1 over cosine square hyperbolic tau. So you can find it. Maybe there's an h somewhere. No, I don't think there's an h. So you can work that out on your own. But remember, there was another set of coordinates. You can do this. So this tau is called conformal time. You can do this transformation in these coordinates too. So again, you can take this scale factor, like do a conformal transformation. And then your coordinate system looks like this. So now this eta is the conformal time. And this ranges from -infinity to 0. So this late time slice, you reach this as t goes to +infinity, or this planar conformal time goes to 0, or that global time goes to +infinity. And you can see in those references I gave in the beginning, those lecture notes and PhD thesis, you can find transformations between all of these coordinates, between the our global coordinates, planar coordinates, this conformal time coordinates. You can find transformations between all of these. And it turns out that this planar patch coordinates here cover this section. Planar patch coordinates cover just half of the Penrose diagram. Well, either this half or like this, it doesn't matter. But just this, what matters is they cover all of late time boundary. So this we will call as boundaries. So planar patch has access to the full late time boundary. Now, this is also why we use these in inflationary studies, because the cosmic microwave background radiation originates towards the end and a little after the end of inflation. So let's draw it by a different color. In some sense, in a way, this is the surface in the coordinate system that CMB observations probe. That's where they have access to. And that's why we make use of this coordinate system. And eventually we always calculations, we always look at the late time limit. So that's the contact with observations. And this system has access to only a single point from the early time. So this is, in the rest of the lectures, this is also the coordinate system we will make use of. This is why if you make a calculation, it will be more like a primordial calculation again. So this was the technical thing I kind of hinted to in the beginning. And there's another set of coordinates that cover this triangle. These are called static patch coordinates. There's a lot of interesting features of these coordinates we will not mention, but these are the coordinates accessible by an observer living in the de Suture era. So as inflationary observers, we are observers with this planar patch coordinates. So this is inflationary observers. But as dark energy observers, we are in this coordinate system. And well, it's like, there's a lot of interesting questions, a lot of techniques we mentioned, especially regarding representations. We will maybe analyze them for in planar patch coordinates, but there's also a lot of work that analyzes them in static patch coordinates, for example. So this is the thing to keep in mind, and this is what we will focus on. So today we just covered the geometry, and tomorrow we will cover the symmetries. And well, let's just to see if you are all there. So for whom all of this was new, like for who all there saw the de Suture Penrose diagram for the first time? You can just make a shape. Or was this all new? Okay, there's some people. So you can just make these kind of shapes. If this was the first time for you, then it means we achieved something. You can look at other, now you can go and look at other Penrose diagrams of other spacetimes.
Gizem, thank you so much. I guess it's a good place to stop right now, I suppose. Before we stop the recording, are there any questions from the audience?
I got a question. I still wonder that the concept of hyperbola. Well, it's a curve, so it has to have one parameter, I think. But as far as I remember, it has two independent parameters. Or am I making a mistake?
I think you can think of this h, that's like, that added things equals something, that number can be anything. So that's the, I guess that can be the parameter. You can think of it.
That's Hubble constant, no?
That's Hubble constant, but that's the physical meaning. So the physical meaning of H for us is the Hubble constant. It's the Hubble constant for the Suture, but this can have value equals 5, value equals 10. So that's the parameter range from one hyperbola to another. You know, you can draw one hyperbola where H was 5, another one as, you know, as a mathematical object with different hyperbolas. It will just correspond to having different H values.
No, but maybe, I mean, I think that's a surface because it has 2 independent parameters. That's why I'm asking that. Not like not a curve.
I mean, I think I understand the question, but maybe I understand that as well. Are you referring to the fact that its surface can be parameterized by 2 parameters, like a sphere?
Yeah, yes.
Okay, yeah. But that's just the parameterization of the surface of the sphere, right? But the sphere has a parameter, just one parameter, radius, r. It's just analog of that.
I understand, So it's actually its surface. Okay, it makes sense.
So again for the interruption.
No, thank you for the interruption. That was good.
Are there any other questions? Okay, then I'm gonna stop the recording, just a second.